Good evening all. Let's get quickly started. Before getting started with today's session, we'll have a brief recap of what we were discussing in the last session. So we started with the convective diffuse equation for a steady state flow. So we have phi equals del dot gamma del phi plus some source term. Say suppose this was the question we were discussing in the last session. So when we have rho and gamma to be constant, and for the case when s equals 0, so we have a domain, and let us say it's a 1D domain. Then we kind of you can write this as I can kind of take it as rho u phi minus gamma del phi equals 0 when s equal to 0, and I can write this term essentially as some j. J is the net flux. Essentially it has both the advective term as well as my diffusion term. So the equation essentially says del dot j bar equals 0, and for the case when we are having one dimension, this essentially comes down to dg dx is 0. So j equals constant, and now we have j written as rho u phi minus gamma d phi dx. So we'll get quickly started. So this was the last problem we were discussing in the last session. So we have our convective diffusion equation. In this particular case, when both the density and the diffusion constant are constant and your source term is 0, this is the equation we'll be ending up with for one-dimensional scenario. In the one-dimensional case, so the solution for phi essentially follows. So we don't have the constant term to be 0. For that particular scenario, we have rho u phi. And this solution for this is say 0 to L. So essentially phi follows So essentially phi follows an exponential profile. So this is the result we came up with in last session. So but when we are assuming, so when we discretize our domain, this is my P cell, this is my E cell, and this is my phase. What we were trying to do is when we discretize this equation, so when we apply over this particular cell for a one cell, for this P cell, so from this we will essentially get rho u phi on the east face minus this is my west central. rho u phi on the west, and then we have my diffusion terms, that is gamma d phi dx on the east face, and then gamma d phi dx on the west face. So in this particular term, u and phi, if the velocity field is known, that is the problem we were solving in last week. If velocity field is already known to us, so this rho u is essentially the mass flux that we already know of. Okay, there are dx term that say that is eliminated. So the problem that remains is to determine the value of phi east. Phi literally is the value of phi on the phase centroid. So this is a function of both my diffusion term. There will be a component from the diffusion. Sorry. So this phi, we were in the last session we discussed there are several methods. So one is the central difference scheme, where you just assume it to be phi plus pp by 2. This is in the central difference scheme. You can also choose to be if you are using an upwind scheme and the flow is in one particular direction. So when the flow is in one particular direction, say in this is my x direction, if the flow is in x direction, then we can assume that all the information from the phi is essentially coming from the point P and not from me. So this will essentially become phi east. This is in the upwind scheme. If the flow is in the positive x direction, otherwise it will be phi, sorry. If the flow is in the positive x direction, it will be phi capital P, and if flow is along positive x, if the flow is along the negative x direction, if the flow is in the negative x direction, then information will be coming from the capital E, so phi will be essentially phi east. This is the upwind scheme. So we have seen that when you write this equation in our standard form, so ultimately we will come up with the equation of this form. AP phi p is sigma A NB phi NB plus B. So when we are writing into this particular form, the coefficient for A east will essentially have terms coming from diffusion as well as my convective terms. Essentially dE will be gamma times delta x by delta, sorry, on the east face it will be gamma delta y by delta x. So if you see on the east face, this is my delta y, this is my delta x. So on the east face, diffusion term will be gamma delta y by delta x, and my convective term will be rho times u on the east face times the area is delta y. So my A east should have some contribution from D east as well as F east. So but how much contribution from each one of them depends on these contributions from each of these terms will essentially determine the type of method you are using. So when we are having CDS, so UDS, and then we also discussed a hybrid scheme and power law scheme. Say we have dE times some function of some function plus the standard form is 0 comma minus Fe. So this essentially takes care of your upwind scheme. So when you purely have pure upwind scheme, you just don't need any okay, that information you capture in this A function, where A is a function of P. P essentially is your Peclet number. Peclet number is essentially your convective by diffusion term, or you can write this as rho u delta x by gamma delta y. The idea behind this is essentially if your Peclet number is too high, then the diffusion term is say if Peclet number tends to infinite, this essentially means your diffusion term is going to 0, and then you can essentially assume the flow to be convection dominant. That is the case we solve when we are using a parallel flow heat exchanger. Even in parallel flow heat exchanger, though the equation are diffusion term in it, but the when it is dominated by convection, you can assume it to be purely convective, and then you can ignore the diffusion terms, and then the problem becomes very similar to time. So even though you have space derivatives dou t dou x, you can kind of assume x to be time variable, and then you can use any of our methods like Euler implicit or explicit form, or you can use Crank-Nicolson scheme to solve the problem. So very similar idea is being used here. So to decide whether the Peclet number is high or no, like once we know the value of Peclet number for each cell, then we use a function capital A of Peclet number. This function will decide how much weightage to give for the diffusion and how much to give for the convective term. So for the central difference scheme, this capital A of P will essentially be 1 minus half into mod P. So we write it in terms of max. So what we mean here is if you have this particular term to be positive, if the flow is in the positive direction, and then the Peclet number is say we will just solve this. So if your Peclet number is less than 2, then 1 minus will be positive. So in that particular scenario, this maximum of 0 comma minus Fe, out of these two, since Fe Peclet number is positive, say it is 0 to 2, in that particular scenario this maximum term will be 0. So this will essentially give you 1 minus dE times 1 minus 0.5 Pe, which is equivalent to dE minus half Fe. That is the same equation that you get in your CDS. Similarly, we have different expressions for upwind scheme. Say in case of upwind scheme, we don't have the diffusion term. So A will essentially be, you can just take it to be 1. So dE plus max of 0 comma minus 1F. In the hybrid scheme, it will be slightly different. So the idea here is CDS is a second order accurate scheme, and UDS is a first order accurate scheme. So what hybrid method takes care is it actually switches between the first and second order depending on the value of your cell Peclet number. If Peclet number is greater than 2, then it assumes UDS. Otherwise, if modulus of Peclet number is greater than 2, it will assume a UDS. Otherwise, if it is less than 2, then it will switch to CDS. So the expression goes as maximum of it will either go to F east, or it will take my diffusion term. So since dE is already here, I am writing just the expression for A. So A will be maximum of 0, and it will take 1 minus, you can use a higher order terms, and then you can also put the other one, so minus Fe. So whichever is a max. So if your convective term is the dominant, then it will consider only the convective term, and your diffusion term will be 0. Otherwise, it will consider only the diffusion term, and your convective term will be 0. Power law is an extension of it. So instead of considering a value of like here we have chosen Peclet number to be the limiting value of Peclet number to be 2 to consider whether it is an upwind or a central difference scheme. But in power law, we will assume it to be value of 10. So we have seen the implementation of this in the last week. So there was one problem we left out, so we will solve that now. So the governing equation is given by this. So we have a one-dimensional distribution of a variable that is governed by both convection and diffusion equation. The governing equation given as follows. The flow field is created by flow in a porous wall duct. So instead of whenever we usually solve in a duct, we usually assume the vertical component to be 0 near the walls, but here it says that it is a porous wall duct, so there is a finite value of the V component, but he already gave the value that mx is the leakage or whatever the seepage is coming through the porous wall. Mx denotes the x direction mass flow rate along the duct at any location x, and mx is the flow rate along x direction, and ml is the rate of mass leakage through the porous walls per unit length of the duct. We have dm by dx is essentially ml. There is no pressure gradient that is driving the flow. The flow is driven by this leakage. The variable phi is some concentration that is being governed by this particular equation. A is the duct's cross section. When ml is positive, if ml is positive, that is fluid is going out, phi L is to be taken as phi, within the duct. When ml is negative, that is fluid is leaking into the duct, phi L is taken to be as phi 0. Phi 0 is essentially the concentration at the outlet, which is the value of phi in the ambient outside the duct. For a duct of length L, the boundary values are given. At x equal to 0, we have phi as phi 1, and x equal to L, we have phi as phi 0. Assuming ml and gamma A to be constant, first part of it asks you to non-dimensionalize the governing equation for phi. We'll start from there. These are the boundary conditions. So we can write x star as x by L, and we can non-dimensionalize phi with respect to phi 1 and phi 0. So we can write phi star as phi minus phi 0 by phi 1 minus phi 0. So if I non-dimensionalize in this way, so we are left with at x equal to 0 is essentially x star equal to 0. So at this particular case, we have phi star to be 1, and when x equals to L, that is x star is essentially 1. When x star is 1, your phi star will be 0. So these will be my new boundary conditions. So mx is also given to us, so essentially dmx by dx is given as minus ml. We will use that as well later. So now we have d by dx star 1 by L times mx. So maybe I can write this directly, so that you have phi 1 minus phi 0 coming out by L times d by dx star mx times phi star, plus you will have another term with respect to phi 0, but the phi 0 derivative with respect to phi 0 is 0, so I am just not writing that. Plus you have ml times phi L. This phi L, I am just writing phi L star right now, because the question says phi L can either be phi or phi naught, depending on whether ml is positive or negative. So it says if ml is positive, then dmx is decreasing. So it asks you to take when ml is positive, phi L is to be taken as phi, and other case when ml is negative, phi L is taken to be phi 0. So my non-dimensional variable phi L star will be phi star if ml is positive, and it will be 0 if ml is negative. I am just writing phi L star minus gamma L by L square so once I write phi star here, so I will have my additional term phi L star into phi 1 minus phi 0 times d square phi star by dx square equals 0. So we can further non-dimensionalize these things. So 1 by L dmx by dx star is essentially minus ml. So if I expand this further and cancel phi1 minus phi0, or maybe we'll leave at this point. So the equation becomes ddx star of mx phi star, and then you have ml phi l star times l minus gamma l by l into d square phi s star by dx star square. So the first part of next part of it asks you to discretize for a given scenario where the values of mx is given at x equal to 0 and x equal to l. Mx at x equal to 0 is given as so if all the parameters are constant, so gamma and all of them are constant, so maybe I can just write directly as, we'll just take the original equation instead of the non-dimensional one. So how do I solve this? So this is my equation, and my objective is to find the value of phi of x given the boundary conditions. So how do I go ahead with it? So these boundary conditions for mx are given. So in this equation, the first unknown is my phi l. To know whether the value of phi l, we need to know the value of ml. So phi l is phi if ml is positive, or it is phi 0 if ml is negative. So but the question gives you only mx, so how do I go about finding ml? We have one more equation, dmx by dx is essentially minus ml. So we can directly solve this equation. So solving this will essentially give you mx is m0 minus ml times x. So now we have the boundary conditions given as here. So at x equal to 0, mx is m0, 40 by gamma a, and then we have at x equal to l, we have mx to be 0, so that gives me l times ml equals n0. So ml is 40 by gamma a. So if gamma and a, gamma is the diffusion constant and a is my area, both are positive, so this ml is positive. So for this particular boundary conditions, ml is positive. So when ml is positive, I should be taking phi l to be value of phi. So my governing equation becomes ml is a constant. I'm just writing ml here, otherwise it will be 40 by gamma a, but you can write it. So phi l will be phi minus okay, now we have this as our governing equation. We already have the boundary conditions, so now the next step is to discretize this equation. So for discretizing the equation, we need to compare it with our standard form. So we have our standard form as, we have a advective term equals convective term plus some source term. So out of these three, so one of them is advective, one of them is the diffusive term, and the other one is basically the source term. which one of them matches to with. So if we compare this equation, this is equation 1 and this is equation 2. If you compare equation 1 and 2, so how do we map this equation, these terms, terms 1 and 2 with our general scalar transport equation? The first term here essentially is del dot, this is my rho u term and this is my phi term. So the first term is essentially an advective term. The second term here is ml times phi, which is something, if we write S as sc plus sp phi, this is the normal source term and this is this sp is essentially, so okay, this entire thing is essentially our source term. So this ml times phi, where ml is a constant, is like our sp term. So this will essentially be my, the second term is essentially my source term, and the last term is the second order derivative, that will essentially be my diffusion term. So as we have been discussing previously, whenever we write my source term as sc plus sp, we have a constraint, like for our Gauss-Seidel method to work properly, we need sp to be negative. So is sp negative in the particular problem that we are discussing right now? Yeah, so here we have sp as minus ml and ml is positive, so this particular term is negative, so our Scarborough will be satisfied and we can use any of our iterative methods. So how do we start with it now? So we will discretize the domain. So we have a domain x equals to 0 to x equals to L. We discretized it. So we'll follow the same notation that we were following previously for diffusion. So we'll start for a general cell and then we'll write the boundary equations. So first say this is my P cell that I am discretizing for. This is my best space. So now writing for the P cell, mxv, this is my source term. I am just writing dv, but here dv is essentially the volume, but we are assuming along y and z directions it will be unit. So dv is essentially dx is gamma d square phi dx square, and then we have minus ml phi dv. So this particular term, if we apply the Gauss divergence theorem, this will essentially be mx phi on the east face minus mx phi on the west face equals this. Again, if we apply the Gauss divergence theorem, so this gives us gamma d phi dx on the east face minus gamma d phi dx on the west face. And the source term, when we are discretizing for the source term, so we just write the value to be equal to the cell centroid. So we will write this as minus ml phi p times the volume. Volume is delta x. So if it is a uniform grid, this I am saying is delta x. Now from here again everything is straightforward. The only thing is we do not, mx is essentially changing with respect to x. So we already have the relation. Mx is given by, ml is again written as m naught by L times x. So m naught into 1 minus x by L, where m naught is given by 40 by gamma A, 1 minus x by L. So or we can write this as x star. X star is our non-dimensional variable. So mx is 40 by gamma A into 1 minus x star. So on the east face, so if this is my cell, this is my x, so mx on the east face is essentially 40 by gamma A into 1 minus x for the east face is cell centroid xp plus delta x by 2. So this gives me the value of mx on the east face, and similarly on the west face it will be 40 by gamma a 1 minus xp minus delta x by 2. So what we are calling the notation that being used in the lectures is, we call this as, this is essentially the mass flux on the east and west faces. So we are denoting it with Fe and this with Fw. So if we write the equations, this will be F east P east minus Fw Pw or Phi west, and for the diffusion terms it's again straightforward. So for the on the east face it will be, we are using linear profile assumption, so phi east minus phi p by delta x, and then on the west face it will be minus phi p minus phi west by delta x, and then we have a source term. So now if we write in the standard form, so we have gamma by delta x, I am just calling it as, on the east face it is d east and d west. In this particular case both d east and d west are same, so we have d east times phi east minus phi p plus gamma times, or we will write again d west times phi west minus phi p, and then we have ml delta x times phi p. Now the next step is to get these phase values in terms of cell centroid values. For that we have to decide which scheme we are going to use, for the reasons that are already discussed in the lecture, which I am not going to repeat. So we will stick to UDS for our discussions, just because it gives you the physical results. And for UDS, so how do we decide? So phi east So on the east cell, like we have discussed, for the east face, if the flow is positive, then you would be taking the value of phi p. If the flow is in the negative direction, then you should be taking the value of phi east. So this will be phi p if my flow is positive, otherwise it will be phi east. So in our scenario, dmx by dx or ml is essentially positive. So this mx here will, this particular term will always be positive. So your x star will be between 0 and 1. So x star is 0 to 1. So mx will always be positive. So your Fe will always be positive. So I can take phi east, phi literally to be phi p. So similarly phi west will be phi p or phi west. So is this positive or negative?
For Fw to be negative, phi W equal to phi p.
If Fw is negative, phi W will be phi p. If it is positive, then it will be phi west. Yeah, thank you. So in our case, Fw is positive, so we will use phi W here. So if we write those equations, so we have F little e times phi p minus F west phi west So now if we group the terms together, like in us to write in the standard form, we have AP phi p is essentially sigma A and B, phi and B plus B. If you were to write in this form, we have A east to be D east, and then we have, I'm just writing 0 times just to stick with our standard format. It will be 0 times max of 0 comma minus Fe. So in our particular case, Fe is positive, so the maximum of 0 and a negative number will be 0. So you will just have DE, that is similar to whatever we have from the above expression. There is only a single coefficient for phi east, and that is D east. So A east will be just D east, and A west will be D west plus, if you write in the form 0 comma Fw. Fw is positive, so it should have both D west and F west. So if you see, there is a coefficient here and a coefficient here. So that is also done. So now AP is written as A east plus A west, and then we also write a mass balance term. So this usually goes to 0. So as we have seen in the original equation itself, this is mass flux on the east flux, this is mass flux on the west phase. So just to satisfy your continuity equation, F east and F west will essentially be 0, the summation of them. So this entire term is your mass imbalance, that will be 0 in usually it will be 0. So your A east plus A west here in this particular scenario is D east plus maximum of this is 0 plus A west
The AP term, what about ML into delta X term, sir?
Yeah, that is that will also be there, the source term minus SP times delta P, SP times delta V, but in this particular case this will be ML times delta X plus. Yeah, thank you. So this comes out to be D east plus D west plus F east. So if you compare the terms here, so you have a DE here for the Phi term, dW for the Phi term, ML into delta X, and then on the other side we have Fe, that is also coming up here. So we have all the terms captured. So we don't have any B terms in this particular problem. If we would have an SC term, then we would have gotten we would have got another B term, but for this particular interior cell we don't have any B term. This is for the interior cells. Now let's see for the boundaries, say on the left boundary. So when I am on the left boundary, if we write the equation, so we have F east phi east first let me write the general equation and then we will see what happens. This is for the interior cells. So when I am at the left boundary, we have phi is equals to phi 1 for this particular case. So out of these terms, phi east again is an unknown, but phi west we know the value of it. We know it as phi 1. So this can be written directly, and then this particular term phi west is something that we do not have here. There is no west cell for the left boundary. So what we do here is we just take the half cell and write the gradient term there. So this term will essentially now become dW times phi p minus phi west boundary by, I am just writing a half here, so it will be 2 times dW. So now the resulting equation is Fe times phi east minus Fw times phi 1 plus we have 2 times d west, phi p minus phi west boundary is phi 1, and then we have our source term. So now again if we write our standard form,
so here after equal to second term minus 2 into dW, no, sir?
Yeah.
The second term after equal.
Yeah, thank you. So if we group the terms again, so we have A east is essentially we have only one term, or we'll write again in the standard form. So east will be same 0 comma minus Fe. A west for this particular case we don't have phi west, so this is 0. So AP should be A east plus A west plus this is in our standard form Fe minus Fw. So now let us see if this is matching or not. So A east is D east and A west is 0 in this particular scenario plus F east minus F west. But if we try to compare the equations, so what are the terms we are getting for AP? So we have a DE here plus 2 dW, yes, and then
ml into delta x.
minus ml into delta x. So if you compare this equation with this, so we need to modify this slightly. So if when you are doing it in, say when you are programming it, so instead of making AW to 0, say let us consider that phi west is essentially phi 1. If you treat phi 1 as your phi west, then what are the coefficients of phi 1 from the above equation?
FW plus 2DW.
FW plus 2DW. So now if we put these equations back here in my AP term, my A east plus I will use this A west term as is, plus I have my F east minus F west. So this gives me, or let us write in the standard form. So we have a DE and DE that is normally coming. Now we have, because of Dirichlet condition, whenever you have a Dirichlet boundary condition, you always have a 2 times dW coming up. If you have instead a Neumann condition, then this term wouldn't be there. And then this FW will get cancelled. This FW is essentially because of the convection on the first boundary. And then we have FE minus FW. To just match with this, I need to put another. So there's supposed to be one FW here as well, right? Okay. If you compare this equation with this equation, so we have a DE term, 2DW, and then you'll always have the other source term. The only difference is your phi east has to be taken care. So FW gets cancelled. There should be a phi east term as well, right?
Yes.
Yeah. This phi east will be essentially phi p. So you have a phi east term coming up here. So both these equations will match. So when you are doing it programmatically, instead of making AW to be 0, you can treat in this way. So like essentially take phi 1 coefficient as that. So AW will be written as FW plus 2DW, so that you can, when you are using Gauss-Seidel method, your Gauss-Seidel will essentially will not know the difference between what is known and unknown. So when you are actually implementing your Gauss-Seidel, you will just be doing phi p is sigma A and B phi and B plus B by AP, and then you just keep changing your value of P, like you will iterate from one cell to the next cell and you keep going on. So it doesn't know whether phi and B is a known one or an unknown one. So what you can do is, if your grid is, so these are my unknowns, you can also add these endpoints, that is your boundary points, into your grid. So now your phi is, say if this is size 4, your phi will be a 4 plus, you have 2 more terms added, it will be size 4 plus 2 by 1. So then you will have phi as 6, but then when you are using Gauss-Seidel, for the phi when it is at the boundary at n equal to 1, n equal to 2, it will consider this boundary as my west cell, and it will appropriately take the AW to be this, and then your Gauss-Seidel will work appropriately. Is that clear?
Yes.
Yeah, thank you. We will see the implementation little later. So now that we have for the left boundary, so similarly for the right boundary, we will not derive right now, so we can directly write the equation. The boundary condition is this is my east face, this is my west face, this is my west cell centroid. So maybe we will write equation directly. So what is my east coefficient, west coefficient, AP, NB. Yeah, by the way, we have a B term here. Now that we have included AW in this, you don't have to separately write the B term, because when you are doing the Gauss-Seidel, what it does is it multiplies AW with phi W. My phi W is considered to be phi 1, so this will be AW times phi 1, and AW is essentially FW plus 2dW times phi1, and that is exactly what we get here. If you compare from this equation, you can write B as 2dW phi1 plus FW phi1. Instead of separately writing it, this naturally comes up in your Gauss seidel. So this is essentially AW times phi1. So you don't have to make this equal to 0. The only thing you have to take care is just not getting confused with this half term that is coming in. If you just write dW, then the half cell that you are considered at the boundary will be gone. So whenever you have a Dirichlet condition, instead of dW, it will be 2dW. That will be the only difference. You don't have to update your B term. That gets automatically included in your Gauss seidel loop. So now for the right boundary, so what will be my equations? Maybe you can tell directly. So T east, this is general, so out of this we know Fe is positive, so this comes out to be dE. West term is again, yeah, by the way, again, sorry. So for the east term, now again it is on the boundary, so you will have, what do I have? A 2 here, and then will I have my east coefficient? Sorry, so I'll write it in the standard way. So I'll just write max of 0 comma minus Fe. Since it is positive, we will not have any terms, and A west is again D west plus max of 0 comma FW. So this will be D west plus FW. So what will be my AP? A east plus AW
plus MX into
minus B term is ideally 0, but here we will be getting, because of your source, you will have, what do you have here? A east times phi is phi 0, so you just take phi 0. So you can derive it in the normal way, so, and just compare this. So we have Fe phi east. So this comes out to be phi east boundary minus phi p by half minus west phi p minus phi west, and then you have, what we are doing is phi east we will replace with phi p, phi west we will replace with yeah. So now if you compare the coefficients, so you have east terms, you won't have any coefficients, and for the west we have dW and FW. AP terms will have 2 times dE will be present, and then you have plus an Fe, yes you have, so is this a plus or a minus? So C minus SP, so it's a plus. So we have, it's minus, right?
If you take to the left hand side, it will go to plus.
It will go to plus. So if I write it on the other side, I have ML delta X, and then what is do I have for the west term? Plus dW. The remaining terms will go into your B. So I have 2 dE, and then I have that's it, only 2 dE times phi EB. That is essentially 2 dE times phi 0. If you compare this with the previous ones, so your FW gets cancelled, so 2 dE plus dW plus, okay, this should be plus here. So you'll have everything similar. So AP is similar, A west is similar, A east will be 0, but we are not doing it that way, so that it is automatically taken care by your Gauss seidel method. So B will be 2 dE times Fe, so that is this is essentially your AE previously, AE times phi 0. So programmatically it is in that way, but when you are maybe for your exam or something, when you are writing, you will be writing in this way. So your A is 0 and your whatever terms come here should will go into your AP term, and the constant will essentially go into your B term. Yeah, I think this is clear. The third part of the question is very similar. The only difference, okay, I think it's okay. The only difference is now your boundary conditions are reversed. So what that means is you will have ML to be negative. So previously we have ML as positive. Now you'll have ML to be negative. So what the governing equation will go as let's write in the standard form directly. So you have gamma a t square phi dx square minus ml phi l. So what we are saying is ml is negative. So what do you think, this will it satisfy our Scarborough criteria if ml is negative?
For ml negative, then L to be
so we need SP to be negative, and here SP is minus ml, and I am saying ml to be negative if you compare it directly. But the question says that whenever ml is negative, you take phi l to be phi 0 instead of phi. So you have phi 0 now. So this entire term will now go into your SC. This is a constant term, so it will go into your SC. It is, and your SP can be taken to be 0. So it doesn't matter if your SC is positive or negative, so you will be able to deal with it. So everything is very similar. Now just that you have SC in your AP term, you don't have ML times delta x. Instead you will be having this in your B term. Maybe we can write the equations directly. So for interior cells, or maybe I'll write it as this: A east, A west, AP, and B. Say for the interior cells. So now you have to remember that in this case, when you discretize this equation, so you will be getting an mx term, that is your flux. But since ml is negative, your flux will be what? Is it positive or negative? Maybe we should derive that first. So I have my equation as dmx by dx is minus ml. This gives me m equals m naught minus ml into x, and the boundary conditions are m at x equal to 0 is m naught is given as 0, at x equal to 0 it is given as 0, and at x equal to L will be minus ml times L minus 40 by gamma A. So ml is minus 40 by gamma A, which is negative. So this gives me m equals ml minus ml is 40 by gamma A times x. This is mx. So this particular term, as your x changes from 0 to 1, even this quantity will be positive. So your flux F east or F west, whatever terms that you take, are all positive. So now with this in mind, you can now tell your expressions. So what will be my A east?
And D plus FW.
For the east term,
Sorry.
Yeah.
0.
And A west?
DW plus FW.
Plus FW. What will be my AP?
AP will be B D plus FC.
DE plus F east. And then for the B term?
For the B term, the S2 term, ML.
I will just have the
ML.
source term. So that is ML times phi 0 times delta x.
Delta.
So I think it will be a negative here. There should be a negative sign here. It's like ml is negative, so it gets cancelled. Okay. Now on the left boundary, we don't have a west, so I'll write directly as 0. So a east will be similar. AP is where your things get changed. So you have d east plus f east. For the east coefficients should remain the same. Now coming to the west term, so what should I get?
That means OP plus FG for the left corner. 2W plus 2W
Plus 2dw.
plus 2dw.
What about my fw term? Will it be there, or it will just get cancelled? It won't be there, right? F west, phi west, your phi west will essentially be constant, so you won't have any terms of f west in this. So what about my b term? So this will be there, ml times phi 0 delta x will be there. And then what else do I have? That's it.
And
Your west coefficient is 0, so there should be some term coming from there.
that means AW into phi AW into phi 1.
Yeah, so that is 2dw plus another convective term. Similarly for the right boundary, your A east will be 0. You have terms from here, so you can write similarly here. It will be dw plus f2 east. Fw will anyway get cancelled. Your remaining terms will come to your b term. So you have phi 0 delta x, and then you will have 2dE times phi 0 here. Is it clear, or did I leave something? There is a f east term also here. There is an f east also here. Or d east f east. So you will have a 2 times diffusion coefficient plus f east. I think that is clear. So now the next question is to solve these equations. So okay, we'll just go through the code. Like instead of solving it with hand, maybe I'll just show you the code that we should have gone through last week. Just give me a second. To those of you who are familiar with Python, so I think you might be aware of NumPy. Just to do some make it easy for you to understand. So it has some matrix operations and array operations that you can do much efficient. And then this is just a plotting library. So the Gauss-Seidel method is again very similar to what we have discussed previously. So you pass in the coefficient AP, A east, A west, and B terms. Phi is your scalar. The tolerance is to let your Gauss-Seidel method know when to stop. So everything is very similar. This is for the east boundary and for the west boundary. I am not just taking the coefficients. So the way of implementation here is I made AW to be 0 instead of actually doing like when we discussed, you could have done in that way as well. Instead of making AW to be 0, you can keep AW as is and then solve. Otherwise you can make AW to be 0 and then update the B value. So I have taken the second approach, that is just to just so that you will get hang of it. Maybe for the next problem we will do it in that way that we have discussed. So if you are at the east west boundary, you do not take A west term. When you are at the east boundary, you do not take the A east term into this. So this error term is to essentially calculate the difference between current update minus the previous value. I have not used any relaxations. So if suppose you are to use any relaxation, say under relaxation or over relaxation, so what you would be doing here is you would also pass in a relaxation value. So I am just saying it as alpha to be 1 here, but ideally you will do that. When we go next to simple, you will be doing this relaxation. So how would you implement it? The idea is when you are doing under relaxation or over relaxation, you do not want to take the complete update as it is. So what you would do is you just take a partial value. and then the remaining from the previous one. So instead of whatever value you get, whatever new value you get, instead of updating it, using it completely, you will just use only the partial value of it to update the as a new update. Most of it will remain previously. If you use a very low value of alpha, your fee will change slowly. That's the whole idea in your under relaxation. You can use over relaxation as well, that which we don't usually do. So I'm just stopping here. So then you have your, sorry, yeah.
But if you take alpha equal to 1, then it will be gas value only, sir. If you take alpha less than 1, then it can be considered
under relaxation. Yes, if alpha equals to 1, it will be the normal one. You don't have any relaxation. Yeah. So I've just put alpha equal to 1 as my default.
Okay.
So now once you define your grid, these are just the number of points and your dx. X is essentially the cell centroid value, locations of cell centroids, and x east and x west have stored those values. X east is like we have seen, xp plus delta x by 2, and x west is xp minus delta x by 2. SC and SP for this particular case, I'm just taking the non-dimensional version. So SP I'm just taking to be minus 1. So I'll update that approximately in my DE term. So here you can either put by 40 times gamma and all of that and update these things instead of that. I have done the reverse way. So if you non-dimensionals, both of them will be similar. So the question gives you SP to be minus 1. Now my coefficients, D east is 1 by 40, it's gamma by delta x. My gamma I am taking as 1 by 40, and D west is also similar. Now instead of calculating phi E and phi W, FE and FW, I am writing the Peclet numbers. This is just to highlight various schemes that we've been using. So like initially when we started discussing, we told like you calculate cell Peclet number first, and if cell Peclet number is greater than 2 or say greater than 10, very high, then you will use upwind scheme, otherwise you will use a central differencing scheme. So just to make use of that, I have defined PE and PW here. PE is essentially FE by DE. FE is 1 minus XE by D east is this, the value that is calculated above, and similarly PW. So first I started using central differencing scheme. So for central difference, what I have done is instead of writing as, so we can write for a central difference, A east can be written as D east minus FE by 2. So instead of directly writing like that, what I have done is use the slightly changed way. So now if you consider the below expression, so if you consider this expression, so minus PE times DE is essentially your flux F east. So this entire term is essentially can be written as max of 0 comma minus FE. So this I'm just removing this so you can easily understand this. So now if the flow is positive, for our particular scenario we have flow to be positive. So what does this term become? So this becomes DE times 1 minus absolute of PE. PE is Peclet number is positive, so it will be 0.5 times PE. Since FE is positive, we don't have the second term. So if we expand this, so you have DE minus half into DE times PE is your FE. So this is what you will be left with. So this is same as your previous expression, DE minus FE by 2. So I've just written it in some way so that you can do this NP dot maximum, will do all of them in parallel. So it just to get some efficiency out of it, like just from a computational perspective, nothing else other than that. So the equations are similar. And then like I have said, whenever you are on the west boundary, I make left boundary, that is your 0, I am making CAW to be 0, and when I am on the east boundary, I am making the n minus 1 to be 0. And AP is essentially sigma A and B plus this is your FE minus FW, and then you have SP times delta X term. Now what we have to do is for the cell boundaries, my AP value has to be updated. Now previously I have made the coefficients to be 0. If I did not make them 0, the coefficients would have automatically been added. Now that I made them 0, I have to add it manually. So what I am doing, at the left boundary you have 2 times DW and then FW times FW, that I am writing as PW times DW. Similarly for the east one, CB is SC times your B term will essentially have SC times this, and then in addition to that you will also have your boundary terms. So these are the boundary terms on the, so we have phi equals to, if we non-dimensionalize, we have phi equal to 1 on the west boundary and phi equal to 0 on the east boundary. So on the east boundary the net addition will be 0 because phi is 0, so only on the west you will have an addition. So then you just call the CFE is essentially you call the solve off, so it solves using the cosine. Now the similar I used an upwind scheme. The only difference is previously we were having 1 minus half into, so this is essentially what we started with. We call this as some a of Peclet number. A is some function that will change with the scheme you are using. For a central differencing, the value of A is 1 minus 0.5 times absolute value of PE, and when you are using upwinding, that is 1. This is when you use an upwinding. Remaining everything will be similar. All the boundary conditions, everything will be similar. The only one is your coefficients will get changed. And then there is a hybrid scheme. So hybrid scheme, like we have discussed, you will switch between CDS and UDS depending on your value of PE. This we discussed even in last class. So we take this expression and see how it works. So if you see, for our case, PE is essentially positive. So this becomes DE times maximum of 0 comma 1 minus 0.5. Absolute of PE is positive, and then the second term will essentially be maximum of 0 comma minus FE. Since FE is, that will essentially be 0, the second one. So you have this particular term. If your cell Peclet number is less than 2, say you have Peclet number less than 2, so in that particular case your 1 minus 0.5 into Peclet number minus 0.5 into Peclet number will be so 1 minus 0.5 into Peclet number will be positive or negative if Peclet number is less than 2.
Yes, I get it.
It will be positive. So my above expression will become DE times 1 minus 0.5 into Peclet number. So that is again your normal equation. So it will be your central difference. The other case, it will be the upwind scheme, so which is usually not the way. So if you take the other scenario where you have PE to be very much higher than 2, then this entire term will go to 0. So you will just have the upwind scheme. So we will discuss that a little later. So maybe in the next question. Next question essentially is that. So that is hybrid scheme. And then there is a power law scheme. This is just an approximation of the previous one, like a better one. So here what you do is you just take DE times maximum of 0 comma, and then you have 1 minus 0.1 P whole power 5, and remaining everything else is similar. So if Peclet number is very small, this you can write this as this can be approximately written as 1 minus 0.5 into P. It's like if you expand it using some binomial expansion or something, this is what you get. So it is a hybrid scheme is a special case of your power law scheme. The other one which I did not discuss is exponential scheme. I have not included that here, but the idea there is instead of using this power laws or anything, you can use directly an exponential function, and then maybe you can go through the reference book provided in the section. So by Patankar, he explains the exponential scheme as well. Usually power law or hybrid is where you will get most physical results, so you don't have to go to exponential. That is computationally more expensive than this. So I stopped with this. Now if you compare all these results from all the methods, so it's the same problem, same grid. So if you compare all these things, so you see the UDS is actually first order accurate, so you expect lesser accuracy to it compared to other methods, and remaining all other methods would give you the physically like all of them are giving you physically meaningful results. You are starting with phi equal to 1, and then it gradually declines. So only when you have these sharp curves, like you might have heard of this called false diffusion. Essentially the problem with UDS is if you have any sharp changes in your profiles, UDS will not be able to capture it, it will try to diffuse it, so it will actually underestimate those ones. So it has a sharp curve, then the predictions from UDS will be off the actual result. Again, the problem with CDS, though it is accurate, it will give you some oscillations. which are not seen here, but maybe I'll show you the next week, where the CDS will actually give you some oscillations. This is the first part of the question when your ML is positive. Now the second part, all the code remains the same. The only difference is your x east and your P and PW. Like as we have seen, Mx is, in the first case it will be 1 minus x times some constant. Here it will be x times some constant. So that's the only change. Remaining everything will be similar. If you just run it, here it has again a sharp turn. So whenever you have these sharp turns, UDS will not be able to capture those, and remaining all methods would be more or less similar. I think I should reduce the grid size. Okay, only 12 or something. I'll post the course so you can go through them later. We'll go to the next question. So are there any questions, or we can go to the next one?
No, sir.
Okay, we'll go to the next question. Next one is a very standard question that we have been discussing from so long. So we have two parallel plates. The only difference between the previous and this one is previous is a one-dimensional problem. Now we will be doing a two-dimensional problem. So we'll have little problems. And then now that you have already been introduced to simple, so we will see how to apply simple here. So we have two plates, and there is a flow between them. Okay. These are the governing equation, continuity equation, and x and y momentum equations. So my unknowns are u, v and p. So three unknowns, three equations, so you should be able to solve them. So these are the boundary conditions. So essentially you are saying you have a uniform flow as my inlet, and then at the outlet I am saying it is fully developed. And the top and bottom, I am saying it follows the no slip for u, and it's not impermeable for v. So I am just saying u equal to 0, v equal to 0 on both top and bottom plates. I am writing u and v as same. Okay. U equal to 0 and v equal to 0 on both top and bottom plates. These are my boundary conditions. So here your v is 0, here your del x of both u and v are 0. These are the boundary conditions. The first part is essentially asking you to discretize it on a staggered grid of size 3 by 3. Okay. So the first part is the difference between the previous question and this question starts here. Is instead of one grid, now we'll be having a slightly different one. So now that you are already introduced to staggered grid, though the question asks you to for a 3 by 3 grid, I am just drawing a 5 by 5 so that you'll have better clarity. So let's say you are having a 5 by 5 grid. So what we do, now we will having 3 grids, one for P, so we have 3 grids now, one for pressure, one for U and one for P. So this pressure is stored at cell centroids, or maybe I'll just write cell. U is stored on east and west faces, V is stored on north and south faces. That is how you approach a staggered grid. We will see the implementation also a little later. So you have so my cell numbering, say I am starting from here. So this is my 1, 1, 1, 2, sorry 2, 1. So this is my I direction and this is my J direction. So any grid is I, J. So I will vary from 1 to nx, and J is varying from 1 to ny. This is for the pressure grid. Say suppose we have uniform one, or it's let's say uniform grid. This is delta x and this is delta y. So any cell centroid xp can be written as I times delta x minus delta x by 2. Or maybe that is easier to understand. So I times delta x minus half. So this will give you xp, and similarly yp. So you can check here. So if you want to get the value here, so it will be 2 times delta x minus this difference is delta x by 2 for the second one. So similarly for any I, this is how you get the cell centroid. And the next one is yp is very similar. So you have, instead of I you will have j, instead of delta x you have delta y. Now how do I store my velocity and u and v velocities? So now if you consider each of these cells, this is my east, here I will store my u, or maybe let me draw a separate so that it will be clear. So I will store my velocities on east and west faces. These are my east face. So slay all the faces. Now the question is, what do I do on this? So like we have discussed previously, you can store velocities here as well. This is essentially the one we are discussing. So when you are using Gauss-Seidel method, so these are my unknowns, but instead I'll add one here and one here also, and use them as boundaries, and then I'll not update my A east, and on the boundary I will not update A east or A west. Now you also need to have velocities on these boundaries. So this is my south boundary and north boundary. So you need to have, I'm just writing here, maybe we'll use a different color. So I will store on the north and south boundaries as well. This is for u. Similarly for the v, instead of the horizontal arrows you will be having vertical arrows. That would be the only difference. So the question is, what will be the size of this u matrix? So when I have my p matrix, it is of size nx by ny. That will be my, say if I will essentially store this in some array. So the size of that array or matrix will be nx by ny. So now this is for u grid. So what will be the size of this? Okay, but before this we will just write xp and yp as well. So in this I will write equations for the this so just as the name implies, this is a staggered grid. So you have these faces aligning with this. So maybe if I put this a little clear. So when I'm writing, when I will try to balance the continuity equation, I will be doing on the cells. My cell will be this. Maybe just one cell is enough. So I'll write equation for only one cell here, or between these two. I'll write equation here, but when I'm writing for continuity, I will solve for one cell here. Just highlighting two cells so that it will be clear. Only for that cell that I will be writing equation for. So when I'm writing these equations for the U grid, so what will be the size of my U matrix? Sorry, I was asking in terms of nx and ny. So like I need to create an array to store this U matrix. So what will be the size of it? Nx plus 1 into ny. So you are having
ny.
7 here. So it should be ny plus 2, right?
Okay.
So 1 on the top, 1 on the bottom. So we'll have 2. So out of these nx plus 1 and ny plus 2, how many unknowns are there? And how many of them are knowns? So what are my interior ones? So interior one starts from 2 to
4.
2 to 5, na? All of them are interior cells. So it will be from 2 to, I'm just using MATLAB notation, or maybe I'll just write 2 to nx are my interior cells. These are my unknowns. And everything else are supposed to be known. Otherwise I will not be able to solve these equations. Or will I be able to solve? So say suppose you are solving a fluid problem, or at least we will consider the parallel plate flow, or maybe say boundary layer flow. So you have boundary layer, so you know the boundary layer flow already. So you have a flat plate and then you have flow here, some uniform flow that is coming in. So now to solve this problem I will have to first define a mesh. So I will say I will put a grid here, something like this. So what boundary condition will I keep on the outlet?
Outlet. Pressure will be kept to 0.
P equals 0, so you will essentially keep it some reference pressure. That will be your reference pressure.
Yes, sir. And you tend to use infinity. You tend to infinity at the last at x equal to L.
No, but in a boundary layer flow you will have a boundary layer like this, right?
Yes, sir.
So u will be a function of y. So you cannot directly put u equal to u infinite. It's like along.
So that means that
here you might keep that, but on the x direction you will not be able to keep that, right? Like at x equal to L, say
yes,
whatever length you have.
X equal to L. Sorry, sir, I don't know what is the boundary condition.
Yeah, so this is something that you will be facing always in CFD. So you need to come up with some boundary condition for your domain. So whenever you fix your domain, you need to give all the boundary conditions. So the advantage here is when we have seen, say even when you are using an upwind scheme, all these values will essentially depend only on the previous nodes. So you don't have to really know the boundary values. If you assume it to be high Peclet number, if P tends to infinity, then there won't be any diffusion term. So to determine the values at the boundary, you need to just know these previous interior cell values. You don't need to know the east boundary if flow is along the positive direction. So as long as you know that flow is in one particular direction, the boundary, this is something you are calling as an outflow. So as long as you know that it is an outflow for sure, then you can use this high Peclet number assumption, and then you will be able to solve it. So that is something that we are doing even here. We are essentially saying it is a fully developed, so you have del u del x equal to 0. Instead of saying u is constant, I am saying as you increase your x, your u will not be changing. So whenever you take your domain, the domain should be sufficiently large to include all the effects that you want to consider. Otherwise you need to give appropriate boundary conditions. So this is some example that even the professor will be discussing. I think he would have discussed. So we'll have some flow over some channel like this. Then you might have some of this, some flow is like this. If flow is happening, then you might have some vortices here. So if your computational domain is sufficiently large, then the outlet conditions will be independent of these conditions, so you can use del by del x equal to 0. Otherwise, if you just consider only a small portion of that boundary, then you need to give these velocities correctly, otherwise your solution will be wrong. Like you will get some solution, but that won't be physical. Yeah, anyway, that is something else. So now where are we? So this is for the U grid. Now similarly we'll have for the V grid. So for the V grid, instead of nx you will have ny, and ny it will be nx. So it will be ny plus 1 or nx plus 2 times ny plus 1. So it's the same. Instead of 2 to nx, you will have 2 to ny as your interior cells along the vertical direction. So now I need to have this many equations to solve this. Okay, now let's come to this problem. So we have first del u del x continuity equation. Continuity equation is discretized on your cell centroids. Discretized essential on your P cell. So I am calling this as U cell and this as my P cell. So this should be straightforward. So you have, this is my P cell, east, west, or okay, just to be familiar with it's like if I read east and west you might get confused, so I will just use indices. So that it will be easy for you to later implement your own codes. So if this is my I comma j cell, east cell centroid is I plus 1 comma j, this will be I minus 1 comma j, and east face I am writing as I plus half comma j, this I am writing as I minus half comma j, south as I comma j minus half, north as I comma j plus half. This could be one way you can use, or you can just follow the same notation. You can call this east west, AP, A east or something like that, that you are already familiar with. Whichever you are comfortable, you can follow that. You can just call this as east, west, north, south. I think sir uses this notation, so maybe I'll stick to this so that you won't get confused when you refer to the lecture later. So we'll stick to this notation only, but when you are implementing in codes you need to use indices, so you can derive it using this also. So continuity equation is straightforward. So when you discretize, what are the terms you will be getting? So though there is no row, even if I put a row, it shouldn't make any difference. So let's assume that row is 1. So this will be f east minus f west plus f north minus f south equal to 0, where f east is u east times delta y. Similarly, f w is u w times delta y. F north and f south are very similar. Continuity equation is straightforward, but we don't use it directly. So next step is where things get slightly different. So we discretize x momentum on U cell. So this is my P cell. This is my east face. This is where my u velocity is stored. This is my east. This is my east east. Say it is my little e. So this is my north face, south face, west face, west cell centroid. Now this I am calling as it is northeast. This is northeast, and similarly here you will have south face, and this I am calling as southeast. So these are the notations we will be following. So now what is the cell I will be solving is this. between P and E. So I need to discretize my equation for that. So what is my x moment equation? This goes like, or you can write it in standard. We'll just follow this: rho u del x plus rho v del u del y. This we have minus del p del x plus mu times so now I'll consider this highlighted portion, and I'm writing discretized equation for that. So we'll just take terms term by term. So when we do for LHS, so I'll just do integration rho u del x plus rho v del u del y times dx dy. So if I write, this can be written as, if rho is constant, so you can just take that out, or is anyway constant, so you can write this as del x rho u plus del y of rho u. So we'll be able to write it in this way. Since there is continuity equation, there will be two more minus, the other terms will just cancel off. So essentially you will have minus rho u times del u del x plus del v del y. I'm just making it to be 0, so this is the equation you get directly. So once you integrate it, you will be having this is where you get your non-linearity. So how do we solve that? So you see the LHS term essentially has, if you integrate it, you will be having rho u on the east face minus the west face times delta y. We have rho uv on the north face minus rho vu on the south face times delta x. So it's non-linear, so we will not be able to solve it as it is in this particular way. So we have to linearize it. So what we do, we will use the very scheme like the deferred correction approach kind of thing. So what we do is we just assume rho u. We will take the value of u and v from the previous iteration, and if you consider that way, so what I was trying to say is rho u east times u east, or you can take the delta y also. So you have rho u east delta y times u east u west plus rho v north delta x u north. Since I am writing x momentum equation, my unknown should be in terms of u east, u west, u north and u south, so I am writing in this way, minus rho v north delta x, sorry, north is already written, so we have south into u south. This is what you will be getting. So what I do, ideally I should be taking the value of current u, but what we do is we just take from the previous iteration values. So this entire terms I am just keeping star, where your star values essentially mean you are taking from the previous iterations. This is again similar to your original equation. So instead of so when we compare with our original scalar transport equation, here you will be having phi east, phi west and phi north, phi south, but instead of phi you are having u. So your scalar is now your horizontal velocity. So Fn un minus Fs us. So this is on the LHS. So now RHS is again, or okay, we will complete LHS completely and then we will go to RHS. So now suppose we are using an upwind scheme. Now the question is, what is value of Fe, though I have written as rho u east times delta y, say u is star, which means when I am discretizing for this particular cell, what is my east face centroid? Where is this U E star calculated? So I am discretizing for the highlighted portion. So east cell centroid is essentially my capital E. So for the highlighted cell, this is my east face centroid. So this U E star should be calculated on the cell centroid, but then we don't have the value calculated at the cell centroid. Instead we are storing all these values only at the face centroids. So now you need to calculate U E star. So I am just approximating it as U E star plus U east by 2 times delta y. So similarly your F west will also be in terms of, if you see the west face, so west face will be in terms of which two face centroids?
Apple and B.
This is my west, so capital W is somewhere else now. So like we are not actually storing velocity values at the cell centroids. We are storing velocity values only at the lowercase values. So I want my value at P. I want my velocity at P. This is my face centered on the west face.
Okay, then W and D.
Little w and little e. So you have U E star plus UW star by 2 times delta y. This is your FW. F east and FW are quite straightforward. So now comes the next part. So F north is rho. Okay, this is U. We'll have V star times delta x. So for this north face centroid is this particular value. How will I get the value there?
E and N. E and N.
So you know E and NE, east and northeast face are actually storing my U values, right?
Yes, sir.
Fn essentially has a V component. Fn is it's the flux along the horizontal face. So your velocity should be perpendicular to your face. You should have your V component. So this is your face.
Okay.
So you should have this velocity like this.
But here it is 0, right?
So my velocity, I need velocity here, but I don't have the velocity stored here. I have my velocity stored here and here.
Yes, sir.
So if this is my north face and this is to the east of north, so I can call this as northeast for V. So then this will essentially come out to be V north star plus V northeast star by 2 times delta x. If you would have used indicial notation, it would have been straightforward. Say if you are using indicial notation, how will you write this? So this will essentially be V north is I j plus half, and northeast will be I plus half j plus half. Sorry. So northeast will be I plus 1 and j plus half. So it is 1 increment to the x and half increment along the y direction. This is if you are using some matrices, which we will see when we actually implement in the code. And then south is again straightforward. So we have, now that we know the north, south should be simple. So what will it be? You can see from here. This is south. If this is southeast, so it will be south and southeast. So or if you write in the indicial form, so it will be V star I j minus half I plus 1 j minus half by 2. So now you have your LHS. The next part is the RHS part. So this should be for this particular case it is straightforward. So you have gamma times gamma is essentially mu here. You have two terms. So you have minus del p del x dx dy, and you also have mu times del square u del x square so this will be delta y times minus delta y times delta p is essentially, if you assume a linear profile assumption, so it will be p east minus p current p. Then you have this mu times del u del x on the east face. So it's again very similar to our previous ones. So you have a delta y times this, then you will have a delta x times del u del y on the north face minus del u del y on the south face. Now again the questions are what are these gradients? So del u del x on the east face. So if you see the cell again, so on the east face, this is my east face, what will be my gradient? What are the corresponding cells? Little e and east east. So when I am trying to calculate the gradient here, I will be using both the left and right terms of it.
Factorial small apple.
Sorry? Yeah, so you will essentially have east east minus east by delta x. Similarly for the west face is also straightforward. Now if you see on the west side, so this is my west face centroid, P is my west face centroid. So for the west face centroid, when I am calculating the gradient, I need to consider cells to the west and east of it, so that will be little w and little e. So this will be ue minus uw by delta x. So if you see u east east is the value of u stored at the east east face, which is again a face centroid. So I have the value of u there, and similarly uw also I have the values are stored at face centroid. So these values I can calculate. What is the value of del u del y on the north face? So if you see on the north face centroid is this particular one. This is my north face centroid. So when I am trying to calculate the u value there, again it is midway between the northeast and the east face. So I will just write it as u northeast minus u east. Instead of delta x, it will be delta y. Similarly on the south face, it will be u little e minus u southeast by delta y. So this is straightforward. Now if you have mu is constant here, you say suppose your mu is varying, so you can have a variable diffusion coefficient, like we have seen some of the problems previously, then you should appropriately take this ones. So if you are at this particular cell, the red color one, if you are at the north cell face centroid, then you need to take the gamma value as say some mean of north and northeast, depending on you have del u del y, so you can take mean of all the PE north and northeast. It's like we have discussed previously, you will be taking harmonic mean instead of arithmetic mean, and then use that as your face centroid, as the value of gamma at the face. So now my equations are, so the RHS, now once I know all these values, I can get my RHS equations. So now I have both my LHS and RHS equations. So finally this again you can write in terms of d east, d west, d north and d south. So d east and d west will be essentially mu times delta y by delta x, and d north and d south will be mu delta x by delta y. So when you write your equations, so again you will write it in a standard format, in our standard form. So you have, I am writing as a little e because my cell centroid is e. So a east, u east can be written as sigma a and b, u and b. Now we have a pressure term plus some b, and now in addition to that we have a pressure term minus delta y times or plus delta y times pp minus p east. The question is what are my NB, or east east, west, northeast, southeast. These will be my neighboring faces. So what are the coefficients? So for the east coefficient, it's again same as what we have done for the convection. So it will be d east plus max of 0 comma minus fe. So everything else is very similar. So if you are using up-main scheme, this is what you will be having. So similarly, your A west, A north and A south, there won't be any differences there. So I'm just writing U as a superscript, so that these are the equations I get when I'm writing when I'm discretizing the U momentum or the X momentum. And AP or AE here, this particular value I'm calling APU, will essentially be A east plus, this is all, everything is very similar to whatever we have done previously. A north, A south, then you have so these are straightforward. Now that you have done for U, similarly you can do for Y momentum also. So when you are solving for Y momentum equation, so your discretization will be so this is my Pth cell. I will discretize for V is stored on the north face. So this is my north. So I will discretize for the half cell, something like this, north to P. This is where I will be discretizing. So to label all the phase centroids. These are my phase centroids. And so all the equations will remain similar. So now you need to calculate the F. So we will write the equations directly. So if for this particular one, my what will be the value of F east? Rho. So east is, you need to calculate at this particular point. So what will I write here? Like previously we have seen, this is northeast. So F east is a horizontal flux, so you need to have U here. So but I need to know the value of U at this point, which I do not know. So I'll use an approximate value of east and northeast. I'll just take U northeast plus U east by 2 times delta y. Both of them are star, so essentially at the previous iteration. So F west, again I need to know at this particular value, so I'll use
NW by
NW and W. So F east and F west are done. Now the next step is your F north and F south. So F north is at capital N. So how will I calculate the value of V at capital N?
VN LN VN plus VNL by 2. VN VN plus VN by 2.
Similarly, you will do for south. South is this, so you have VN and VS. So now you have all your F. Next step is to, your D east, D west, D north and D south are again the same as previous one. So all your expressions are similar. You have your A east will be D east plus maximum of 0 comma minus FE. Like everything is very similar to whatever we have done previously. So AB will be sigma A and B plus F east minus F west plus F north minus F south. The only difference, instead of U, you will be having V here. So now I have now the question is, these are for the interior cells. First you do the discretization for the interior cells. Now for the boundary cells. Let's take one boundary. Say we are taking the left boundary. As we have seen, so say this is my current cell. So here is my velocity being stored. So first let's say we are solving for the X momentum boundary equations. So my U is stored here and also here. So like the way I am storing the boundary values also here. So I know this value also. So when I am discretizing the cell for this particular cell, okay, it seems like I lost the connection, so maybe I'll upload the recorded lecture. So I'll just show you some of the implementation of this code now. Now since I have left this connection and we have 10 more minutes left, I'll just go through some of the implementation details of x and y momentum equation. We will discuss about the boundary conditions a little later, maybe in the next session. So I'll just quickly go through some of these codes. So this is for the case of boundary layer equation that we discussed in the last week. So this is just a helper function. So range is, it will just give you a range of values between say 1 and 10 or some whatever range you give, start, step and your stop. So max is just now that we know that depending on your type of scheme we are using this function a lot, so I've just defined a helper function for max, and this is just to give a matrix. So matrix is one helper class that functions are very similar to what you do are using NumPy. So as I have defined, so x and y are the cell centroids for all the interior cells, and x2 and yv are for the x component of velocity and y component of velocity respectively. So what I have done, like what I have shown previously to you, so your u component has a size of nx plus 2 comma and nx plus 1 by ny plus 2. So these are the u and v components that I have stored here. Now what I am doing, now in this u and v, every time when I am writing the cell equations, I will be writing only for the interior cells. So now I am just storing all these interior cells in this particular array and u. So Ju is essentially from 2 to ny plus 1, and similar Ju is essentially the j component of u, and iv is for the v component, so it will be from 2 to n. So essentially what I mean by this is 2 to n, so u varies up to ny plus 2. So out of this ny plus 2, the first and the last one are reserved for the boundary. So I am having a south boundary and a north boundary. So my interior cells will only range from 2 to ny plus 1. I have not written along the x direction because we will see later that as we have discussed previously, in the Gauss-Seidel loop that will get automatically involved, so I am leaving that aside. And why am I treating south and north boundaries separate is because the way we have defined it, the south and north boundaries will have mostly, say if they have Dirichlet condition, you will have a 2 times diffusion coefficient, so I don't want to include them directly. So I will treat them separately. That's why I have kept this, I am updating only from 2 to ny plus 1. Similarly for the V component, you will have east and west as the Dirichlet conditions usually. So the north and south will be in a different way. So IP and JP are for all other cells, for your interior cells. IF and JF is the one that you have discussing. So when you have having interior cells, your U varies from 1 to nx plus 1. So out of this 1 to nx plus 1, the first and the last one are reserved for the east and the say west and the east boundaries respectively. So my interior cells will only will be from 2 to nx. Yeah, so I think there was some network issue and I got disconnected. So I was just thinking like before discussing the boundaries, now that we have just 5 minutes of time, so I'll just quickly go through some of this implementation. We will discuss boundaries maybe in the next session. So as we have discussed, so your U will be essentially an array of nx plus 1 by ny plus 2 size, and V will be of nx plus 2 and ny plus 1. I am storing some other values like u star and v star were essentially the previous values, that the values of u and v that you will get after solving your momentum equation. U prime and v prime are for the velocity corrections. This du and dv are the, when you write the pressure correction equations, you will have these coefficients written in terms of du and dv. So these are those terms. P and p prime are very like p is for your pressure and p prime is for your pressure corrections. So I've written here also nx plus 2 and ny plus 2 because you will be having boundaries for pressure also. So I'm just incrementing the, when you have your unknowns from 1 to nx, I'm putting 1 to the left, 1 to the right.
Sir, your voice is not audible, sir.
Yeah, sorry, am I audible now? Yeah, I think I'm on mute.
Yes.
I was on mute. Okay. Yeah, so what I was saying is I've just declared these arrays of whatever size we have discussed. So u will be nx plus 1 and ny plus 2, and v will be nx plus 2 and ny plus 1. Similarly, u star and v star are the velocities you obtain after solving your momentum equation. U prime and v prime are the velocity correction equations. Du dv are the coefficients of the pressure correction equations. And even for p, what I am doing is I am adding my boundaries on the left, right and top and bottom. So instead of nx times ny, I am adding a 2 and 2 here. So like left and right, top and bottom. Similarly, p prime is for your pressure corrections. The next step is your fe, f west, f north and f south. Essentially when you have n cell centroids, then you will be having n plus 1 faces. So these sizes f east and f west will be stored on all the faces. So I am just giving a size of, that will be the maximum size, nx plus 1 and ny plus 1. And then you have df. df is your mass imbalance term. dx dy are your diffusion coefficients. Your d east, d west and d north, d south. So ds, d west, d east and d west I am calling dx, and north and south I am calling dy. So yeah, we'll have to update these coefficients. Okay, we are almost out of time. So maybe we'll take it up in the next session. So how to update the coefficients and how do we solve this? Maybe we'll first do it on a paper and then we'll come back to this. So before closing, do you have any other specific doubts? There were some questions on diffusion and something else in the discussion forum. Are there any other questions? And we can discuss it. Maybe we have a couple of minutes left. If you have any specific questions, we can discuss them.
I mean, for knowing the Python very well, what we have to do, sir? That means Python.
So like, have you had any experience with any other programming languages other than Python?
I have experience in MATLAB, sir. I can do program in MATLAB.
You are familiar with MATLAB already?
Yes, sir. Whatever program you teach before up to 6 weeks, 6 to 7 weeks, I performed in MATLAB, sir.
Yeah, then it should be it's like you can just do in the MATLAB. It's like if you get the logic, you can do in MATLAB itself. The one I will be seeing for simple is C++. That code will be very similar to your MATLAB version. You can directly implement it.
So, but in MATLAB, for 3D, how we can do in MATLAB that I can't understand.
You can store matrices in 3D in MATLAB as well. It's like MATLAB allows you to store a matrix, right? You can store 3D matrices there. You will have 3 different indices, I, J, K. MATLAB allows that.
Okay.
Might be a little tricky with this, but MATLAB allows for 3D as well.
I mean, up to now, I only do 2D problems only, but I don't know how to do 3D problems in MATLAB. But I want to learn Python to do things. But I want to learn the Python to do the 3D problem.
In Python, if you are using NumPy, that gives you similar functionality as your MATLAB matrices. So you will be able to do 3D there as well.
What is the platform to learn the Python, sir? Very well.
You can refer any W3 schools is one website to learn. Like if you are doing it in online, like there are so many websites, tutorial point in W3 schools or something from where you can learn. But for this particular course, for this particular course, you just need to know some libraries. Say like NumPy is one that you will be knowing to deal with matrices. That will be very similar to your MATLAB.
Okay.
So I have uploaded some Python codes, so you can go through them in the last week. So in
Yes.
you can go through the course. If you have any doubts, we can discuss in the next session. So
Okay.
it will be very similar to MATLAB. You will have some additional functions before it, but other than that, plus like all other operations will be very similar to MATLAB.
Yes. Okay.
So you go through the code and let me know if you have any questions. You can post in the discussion form. Maybe we can address it later.
Okay.
Okay then. If there are no other questions, then we can end the session for today.
Thank you.
Yeah. Thank you for joining.